In this video, we're going to talk about shift register. And what is a shift register? Now, register basically flip-flops. They are connected, right, in sequence, right, and they are used to store and transfer data. Now, take note that whatever that we have been talking about shifting data or storing data, so far we are talking about 1 bit. Now, if I have actually a 4-bit data or maybe 8-bit data, right, so we will need shift registers, right, to actually store the data. Then after that, when the data needs to be sent to the output, right, then the data can be sent out one by one, or it can be sent out all at once. Okay, right, so there are 4 different types of shift register, right? Whether the data is coming in serially, meaning one by one, right? Let's say if you have a 4-bit data, so imagine that one bit by bit, right, that data is being transferred to this shift register and stored, right? Or you can also have parallel, right? So the 4 bits, right, from a data is stored at the same time, right? And in a similar case, the output can also exit in a serial way or a parallel way. So there are 4 different types of shift register, right? So the first one that we're going to talk about is the SISO, which is serial in, serial out. So what's happening is the data that you have will be going into this shift register 1 bit by 1 bit, and you exit this shift register 1 bit by 1 bit. Now, so the question comes, right? What is the purpose, right? If it's shifting in 1 bit by 1 bit and shifting out 1 bit by 1 bit. So everything here has to do with the clock, right, and synchronization. So example, if the bits are coming in at a different timing, so you want it to be synchronized before the data is being sent out. Right, so for the first serial in, serial out shift register, right, the D flip-flops are connected in series. Right, so what is happening here is on the positive going transition, right, or we call that the rising edge, right, data is loaded bit by bit. Every data bit is loaded serially until all the bits in one packet are loaded. For example, this case here, right, you have 4 flip-flops here, so I can actually store 4-bit data packet, right? Now, so the number of flip-flops will be determined by the number of bits in one data packet. So in a 4-bit data packet, you will have 4 D flip-flops here. Right, so the thing is, why are we using D flip-flop? Because a D flip-flop, right, will actually follow the input, right, every time the clock triggers. Okay, so basically, so it will just make the data get synchronized. Now, so the data will exit the register 1 bit at a time, right, in the same order that it is being original loaded. Okay, so if you think from a D flip-flop perspective, right, whatever that comes to the input, then at the next PGT or the rising edge, then the output will be equals to the input, right? So if you have a 4-bit data packet, you will require 4 clock cycles, right, for it to complete the entire process, okay, of shifting all the data into the registers one by one. Right, let's take an example here, right? So I have a SISO and I'm shifting a 4-bit code in and out of the register, right? So what is that 4-bit code that I want to shift in? It will be 1010, right? So this is the LSB and this is the MSB. Now, so what's happening here is initially, right, all the Q0 to Q3, right, they are all zeros. So we can say that it's all being reset. So everything here is 0, 0. Let's put that down. Okay, 0, 0, 0, and 0 at the very beginning. So what happened here is we are going to start storing the data. So what happens here is I'm going to put the LSB data bit, right, into the serial data input first, right? So I'm going to put a 0 here. Right, then at the next clock cycle, right, then the output of the first of the FF0 flip-flop 0 will change its output, right, to a 0, which mirrors this input. So this is what happens at the first clock cycle, right? Then at the next clock cycle, right, the serial data is going to 1 will be at the serial data input. But we're going to talk about that one later now. At the second clock cycle, what's going to happen is the output from the flip-flop 0 is going to be tied to the input of the next flip-flop, flip-flop 1. So at the next clock cycle, 0 will be stored at the output of flip-flop 1, right? So this will be 0. And right at the same time, due to the clock action, the data that is at the input will be at the output of flip-flop 0 at the positive clock cycle, right? Now then what's going to happen next is the before the next clock cycle, let's say the second MSB, right, is then put at the serial data input, right? Then at the next clock cycle, right, so we're going to go to flip-flop 2 first, then flip-flop 1, then flip-flop 0. Okay, so at the input of flip-flop 2, right, the input is at 0. So at the next positive clock cycle, the output will then become a 0. Then for flip-flop 1, the input is a 1, so the output will become a 1. And whatever that I have for flip-flop 0, the output, it will now become 0 because the input of flip-flop 0 is 0. Now then before the next clock cycle, then the MSB, which is 1, right, is being fed to the input of the flip-flop 0, right? Then at the next clock cycle, so what's going to happen is then the output of flip-flop 3 will now be 0 because the input is a 0, and then so on and so forth, right? The input of flip-flop 2 is a 1, then the output will be a 1, right? Then the flip-flop 1 output will become a 0. Okay, the output from of flip-flop 0 will become a 1, right? So what I have done here, right, is that now the data is being stored already. Okay, so let's take a look at what's happening here. So the initial, right, at the initial state, right, this was a reset, or maybe it has been in a the flip-flops have been in a are all zeros right at the very beginning. Maybe it has been in this mode for quite some time. So now there is an instruction to store incoming 4-bit data. So what's going to happen is the serial data input, right, we are going to feed the LSB first, right? So at the first clock cycle, right, the output of the flip-flop 0 will become a 0, which is the LSB, right? Then at the next clock cycle, flip-flop 1 will now store the LSB. Then the serial data input, which is holding the input is a 1. Okay, the output of the flip-flop 0 will now become 1, right? Then so on and so forth, right? So at the end, what you have here is that Q3, Q2, Q1, Q0 would have stored, right, the 4-bit data. So we have completed the storing cycle, right, for this 4-bit shift register. So now let's continue to the shifting out of this data. So imagine I have stored 1010 using the 4 flip-flops, right? So basically we started off with storing the LSB, then the second LSB, then the second MSB, then the first MSB, okay, in that sequence. So now I have 1010 with this as your LSB. Now, so what happens is, say I want this data now to come out from the shift register, right? So what I need to do here, right, is I will need to use the clock to shift this data out, right? So because each of these flip-flop will execute its action upon the positive gate transition or the rising edge of the clock, right? So what I have here, right, this is the initial. I have 1010 already stored in each of these flip-flops, D flip-flops. So at the next clock cycle, so what's going to happen is the output of flip-flop 3 will now take the input which is at 1. Okay, so we have this, right? At the next clock cycle, right? Then the flip-flop number 3, right? The flip-flop number 3 output will become a 1, right? Because the input here is a 1, right? Then what happens to the flip-flop 2, right? Because the input of the flip-flop 2 is a 0, then the output at the next clock cycle becomes a 0, right? Then the next one is flip-flop 1. The input at flip-flop 1 is a 1, right? So at the next clock cycle, it becomes a 1, right? Then what happens then to the flip-flop 0, right? Because the moment that the 0 data input is completed shifting out, right? So you are going to put 0 data input to a 0, and this 0 is not part of the data, right? So I have already shifted out the first bit, right? I've shifted out the first bit here. So basically what I have here, right, is that the 0, right, is already shifted out to whichever device that's waiting. So this is my LSB, right? Then I will have 1, 0, 1. Now whatever that comes after this, right, these are not part of the data. This is not part of the data. Now of course you can link the second 4-bit, shift it in as well, right? But at this point of time, we are just saying, oh, we just want to shift a 4-bit data. Then after that, that's all. Okay, so whatever that we are having here is we are just saying that whatever that comes after this will just be a string of zeros until the next 4-bit data comes in. Now, so let's continue looking at what happens at the next clock cycle. Again, at the next clock cycle, right, the input of flip-flop 3 is a 0, and that will become the output at the next clock cycle. So this will become a 0, right? This will become a 0 at the next clock cycle, right? Then because the input of flip-flop 2 is a 1 at the next clock cycle, the output will become a 1. And whatever that I have for the flip-flop 1, the input is a 0, right? Then the output will become a 0, right? So these are not data. Then now I have the second LSB being pushed out, right, of the shift register, right, to whichever device is waiting, right? So so this whole thing just continue, and at the end, right, your shift register has been resetted again, right? So everything will be zeros. Okay, so at the end, 1010 will be transferred out of the shift register, and the device will have received the 4-bit data packet. So we have an example here to show the serial in, serial out shift register operation. Now the data set that we are using is 0, 1, 0, 1, 1, whereby this is the LSB and this is the MSB. So you can see at the first clock cycle, we are loading in the LSB, and at the last clock cycle, we are trying to load in the MSB. Now, so usually the data input needs to be ready before the on the outgoing clock cycle. So let's take a look at this. Q0 is actually missing, so please put in the Q0. Now, so imagine that this register, this 5-bit register, was reset at the very beginning. So all the outputs of the flip-flops are going to be zeros, right? Initially zeros. Now at the first clock cycle here, right, the data input is a 1, right? Then after the flip-flop processes this, the output Q0 will be a 1. Now just imagine that the propagation delay of the flip-flop is close to 0 or negligible. So what we are going to have is that the output Q0 will become a 1 at the very beginning. Now then this 1 is going to be there until the next outgoing transition. Right, then because the Q0 output was a 0 at the very beginning, right, so Q1 will remain to be 0, Q2 will remain to be 0, Q3 will remain to be 0, Q4 remains 0. Now at the next clock cycle, right, you can see that the second LSB is now at the data input, so your Q0 remains as 1. And now Q1 because the output Q0 is a 1, so at the next clock cycle it will become a 1. Right. Then after that, for Q2, Q1 was a 0 before that, so the 0 gets propagated, right? So same as Q3 and Q4. Now let's take a look at the next clock cycle then. At the next clock cycle, right, on the outgoing transition, your data input is a 0. So you can see that the data input was set to 0 much earlier than the clock cycle or the outgoing transition, right, or the rising edge, right? So at this moment, after the propagation delay, Q0 is going to drop to 0. But before that, right, the output was of Q0, right? When during the rising edge, your Q0 output was still a 1, right? So this one Q1 will continue to be a 1, right? Then let's take a look at the Q2. Q1 output was a 1, right? So at the next rising edge, Q2 will become a 1, right? So on and so forth. Okay, if you understand what is going on here, right, you can see that basically it's just like a relay action, right? So imagine that this is like a relay whereby the person is passing on the data from one to the other, and it will take the next clock cycle before the data gets transferred to the next flip-flop. Right, then at the next one, the data input here is a 1, then Q0 goes up first, right? Then now Q1 will now be 0, right? Q2 continues be a 1, right? Then Q3 now becomes a 1, Q4 remains as a 0. Now at the last rising edge, right, the input is now a 0, so Q0 after the propagation delay of the flip-flop is going to go back down to 0, right? Then Q1 will go up to become a 1, right? Then Q2 will become a 0, right? Then Q3 continues to be a 1, and the next clock cycle Q4 becomes a 1. So what do I have here, right? Let's write down the 0, 1, 0, 1, 1, right? So you can see that the MSB is now at the output of Q0 and the LSB is at the output of Q4. So at this moment, right, the register has stored the 5-bit data in Q4 to Q0 respectively. Okay, now so if it's arranged in such a way that the clock cycles will continues to go have a rising edge, at the next rising edge, right, then it will start to go into the exit mode, or you are shifting the data out of the register, right? So whatever we have done up to this point is we are shifting in the data bit by bit into the register. Now the next shift register that we are going to talk about is the serial in parallel out shift register. Now again, these flip-flops are going to be connected in series, right? This is for the serial in, because we are loading in the data, right, bit by bit. But what do we want? We want this time round to be a parallel output. So it means that at the end, after the data has been shifted in, you want the output to be available to whichever device 4-bit at the same time. Right? So this 4-bit this 4-bit needs to be available at the output of the flip-flops, and then from there this data can be transferred out, right, in a parallel mode. That means all at the same time, so it's not shifting out serially, okay, like the SISO, right? So what happens here is the loading in part is still the same. Every data bit is going to be loaded serially, right, until all the bits in one packet are loaded. So example, if I need to load a 4-bit data packet, so you need 4 clock cycles to complete, right? So at the moment that the 4 clock cycles is completed, right, then after that, then you can then you can access the data at the next clock cycle, okay, simultaneously, meaning that you can access all 4 bits in one shot, right? So now, so let's take a look at the circuit that we have here. You can see slight difference here in that Q0, Q1, Q2, Q3 have leads coming out from it, right? So previously what you have is you do not have all these leads coming out, but now because you want to access the data one shot, right? So you have a Q0, Q1, Q2 leads compared to just now whereby you only have a Q3 lead. So if you, from a circuit point of view, the only difference is that at each of the flip-flop output here, the output is being connected to the external device. Right, so let's take a look at the operation of the 4-bit serial in parallel out shift register. Okay, so right, so the data that we are going to load in here, right, is the 0110, which starts from here. So this is the MSB and this is the LSB. The LSB is the one that we are going to load in first. This question, there is a slight difference here because they say that the register initially contains all ones, right? So we are going to say that your Q0, Q1, Q2, Q3 are storing ones at the very beginning, right? So at a logic high. Now at the next clock cycle, what happens is Q0 will change because the data input at the first flip-flop is a 0. So Q0 output will become a 0 first, right? While Q1 will remain as 1, Q2 remain as 1, Q3 remains as 1. Okay, at the next clock cycle, the data input has been changed to a 1, so Q0 will follow that after the propagation delay, right? And at the next clock cycle, Q1 actually becomes 0 because the input to it is a 0, right? Then what happens to the Q2? Q2 will continue to be a 1 because Q1 output is a 1, right? Q3 no change, right? At the next clock cycle, again a 1 is loaded at the data input, so Q0 continues to be a 1, right? Then now Q0 output is a 1, right? So at the next clock cycle, Q1 becomes a 1, and so on and so forth, right? So we can complete the diagram here quite easily. So let's go to the last clock cycle. So at the last clock cycle, right, the input, the data input is a 0, so Q0 will drop to a 0, and Q1 will continue to remain as 1 because output of Q0 is a 1, right? Then we can continue drawing, right? So this is what you have here. Now what I have at the output now will be 0, 1, 1, 0, whereby this is the LSB and this is the MSB. Now, so at the next clock cycle, so the data Q0, Q1, Q2, Q3 will all be ready. So I have a 0, 1, 1, 0 stored in this register, and you can access this all at one shot. Okay, so this is a serial in parallel out shift register. Now the next shift register is a PIPO, parallel in parallel out shift register. Now so for this one there isn't much to illustrate, because if you look at it, right, it is just 4 D flip-flops which are independent of each other, right? So what happens is at the clock cycle, you can see that the D0 to D3, right, the data, this is a parallel data input, so each of the input is loaded. I will have say this is the MSB and this is the LSB. So whatever data that is at the input of each of the D flip-flops, at the next clock cycle, right, it will appear at the outputs, right? So this is a very simple circuit. It is just independent 4 different independent D flip-flops, right, which will load, okay, and output the data. So this is the simplest design, right, for the parallel in parallel out shift register. This is the simplest among the 4. Now the last one that we have, right, is the most complicated one, because what is required here is a parallel in and a series out. So this is going to be the most complicated shift registers that you will be learning, right? So So if you look at the input here, we are going to have parallel input and serial output. So storing in is going to be parallel, right? But when you are going to shift the data out, is going to be series, right? So every data bit, right, is loaded simultaneously, right, into the shift register. Right, once the data is being stored, right, the serial output, right, is the same, right, as the serial in and serial out register. Now, so this is going to be a little bit more challenging as compared to the remaining questions, but we're going to go through this by looking at the shifting operation and the loading, the shifting operation and the loading operation separately, right? So we have in this design here, you have 4 data lines here. You can see here that there are 4 data lines coming in, right? So this is, then I have the shift and load command here, right? So whether do I want to load the data or whether I want to shift the data. So this is a very, very interesting circuit here, because I will need, right, I will need to shift, I will need to load the data in, and in a parallel format. Then after that, I need to shift the data out in a series format. Now let's take a look at the first scenario, right? So the first one is the loading operation. Now, so what is the loading operation? Which means that I'm going to load a 4-bit data into this shift register. Now, so how do you read this when I say shift slash load bar is equals to a 0, right? So you can take it as shift equals to 0, load bar equals to 0, but load is 1. So whatever that we are doing here is we are loading data, right, into this circuit, right? So now let's take a look at what is happening here. Now, so when this is equals to a 0, right, so we have to ask ourselves which are the gates that will be enabled. Now we have to look at this circuit that we have here, this gate that we have here. This is actually a NOT gate, right? The other version of the NOT gate, because if you still recall, if I have a NOT gate that goes this way, they are actually equivalent, right? So this is a NOT gate. Now, so if this is a 0 and this is a NOT gate, so what's happening here is that the logic here will be high, right? Now, so once I have the 1 here, 1 here, 1 here, and 1 here, then let's take a look at the other line here. So the other line here, you can see that this is going to be a 0, right? And if this is a 0, right, this will be a 0. Now straight away I can say that these AND gates will be disabled, because a AND gate, so long as any of the input is a 0, the output will be a 0. Now let's continue with the explanation here. So which are the gates, which are the AND gates that are actually enabled here is G1 to G4, right? Why do I say that they are enabled? Because one of the input is a 1. Then what will be the output here, right? If the one of the input is a 1, then the output of this AND gate will just depend on what the other signal is going to be, right? Because each of these AND gate, right, is one of the input is a 1, right? So the output of each of these AND gate will just depend on what D0 is. So if D0 is a D0, D1, D2, D3. So in this case, if D0 is a 0, the output of this is 0. If D0 is a 1, the output of this is a 1. So you can see that the output of the G1 is going to mirror the D0. Okay, and same thing, this is going to be D1, D2, and D3. Now whatever that you are doing here, right, you see that when we put shift slash load bar equals to 0, you're actually loading in the data D0 to D3 into the flip-flops here, right? So for the first flip-flop, right, this is very obvious already. This is very, very simple. So the first flip-flop, D0 is loaded to the input of the flip-flop 0, and at the next rising edge, Q0 will be equals to D0, right? But let's take a look at the rest of these. right? You can see that there is a OR gate here, right? This additional OR gate, later we'll explain what is the purpose here. But at this stage, you can see that because this is OR gate, and because the output of these are going to be zeros, right? So the output of the OR gate here will depend on what D1 is, because the other input is already 0. So we can see that, oh, D1 will be the deciding guy, right? So if D1 is a 0, right, then the output here will be a 0. If D1 here is a 1, then this will be 1, right? So whatever output I have here mirrors what D1 is going to be, right? So again, we have a situation whereby D0, D1, D2, D3 is now loaded to the input of each flip-flop. Right. So this is the loading action. So the moment I do shift equals to 0, I've enabled G1, G2, G3, and G4, and the data D0 to D3 are now at the input of each of the flip-flops. So when a clock pulse is applied, then at the rising edge, right, the flip-flops with D equals to 1 will set, right, or will become 1, and those with D equal to 0 will reset. That means the output becomes a 0, right? So what are you doing here? You're actually loading or storing, right, all 4 bits simultaneously. Right, now I have completed the loading operation. So now let's take a look at the shifting operation. How does this circuit complete the shifting operation? So now I have the data Q0, Q1, Q2, Q3 to be equals to D0, D1, D2, D3. Now we are going to check how do I do the shifting. Now the moment that I put shift equals to high or load bar equals to high, it means that load is equal to 0. So we are going into the shifting mode, right? And the first thing that you should be looking at is which of the AND gates here will be activated and which will not be, right? So let's take a look at this, right? So if shift is equals to a 1, output here will be zeros, and the input here will be 1, right? So what do I have? This gate is at disabled, 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 and disabled. Right, so I have 4 gates that are disabled. These are going to be G1, G4 are disabled, and which one are enabled? G5 to G7 are enabled. Right, so now what's going to happen here is that now don't forget that Q0 is equals to D0, Q1 equals to D1, Q2 equals to D2, and Q3 equals to D3 previously, right? So now D0, D1, D2, D3 are actually stored inside these registers. So at the next clock cycle, so what is happening is that, okay, the D0 is going to go into this AND gate here. So this will be D0 here. And because the other input of the AND gate is already at 1, so this is going to, the output of the G5 is just going to be dependent on what D0 is, right? And we already know that the output of G2 will be a 0, right? Then the output of the OR gate after that, it will just depend on what D0 is, okay? Right, similarly, we have the D1 here and D2 here. Now, so what's going to happen at the next clock cycle? Right, at the next clock cycle, right, then we are going to look at the phi n here first. So D3 will already be available to the device. This is going to be the LSB, right? So at the next rising edge, so the D3, okay, will mirror what the input is going to be. So this will be D2 now, right? Then what do I have for the flip-flop 2, right? At the rising edge, right? D2, Q2 output will be equals to D1, right? Then at the next clock cycle, so the Q1 output will be equals to D0. right? So this is, you can see that the data has been shifted to the right, 1 bit by 1 bit. So basically what we have here, right, is that the data bits are shifting to the right, okay, bit by bit. Okay, so what we have here, right, the OR gate actually allows the loading or shifting operation. Now you can see that the flip-flop 0 has only one single N, right, to disable the parallel input D0. Okay, so the AND or OR arrangement is not required because there is no serial data coming in. So there is only serial data out but not serial data in. Now, so what do I have here, right? This is a 4-bit PISO shift register. We have an example here, right? Now you can see that the circuitry has been simplified, and whatever that you have here is just a block diagram, right? A block diagram of what the 4-bit shift register actually looks like. Now, so I would like to just simplify everything by just pointing out what data out is going to be for Q3. Right, so these are the data 1010, which is loaded into the shift register. Right, so what's going to happen here is, imagine, let's take a look at this, the signal shift slash load bar, right? So you have to ask yourself, at clock cycle 1, 2, 3, 4, 5, 6, what operation is it in, right? So if you observe, right, at the very first clock cycle, shift or load bar is a 0. That means you are doing a load action at this point, right? Then after that, at the 2 to 5, you are actually doing a shift operation, right? Now, so what do I have here is this. At the first clock pulse, okay, you are doing a loading action, right? So D0, D1, D2, D3, which is 1010, is being loaded into the register. Now, then what happens here is, at the second clock cycle, what is happening, right? We are going to, before that, let's just say that the data out at the very beginning, right, will be a 0, right? To make things simple, let's say it's a 0. Right, at the first clock cycle, so what's going to happen is that the 0 will be loaded into Q3 already. Right, so this is the first 0 that you are looking at. Right, at the clock. So now let's go to the clock pulse number 2. Right, clock pulse number 2. So what is happening is we are shifting 1 bit. Right, so Q2 is shifted. The output of Q2 is shifted into Q3. Right, so what happens then is that the output of Q3 now becomes 1, as the input to it was a 1 from the second, from D2. Right, then after that, what do we have at clock pulse number 3? Right, at clock pulse number 3, right, then you have a 0 that is shifted to your D2 now. Okay, maybe I should change this, because this is now 101. Right, so D2, the output is 0, right? So that gets shifted into the D3, and now the output of D3 is a 0 now, right? Okay, what do we have here? This is going to be 10 already, right? Then the next one will be a 1, because the D2 output is a 1, then that goes into the D3 input, and now D3 becomes a 1, right? So at clock number 3, right, 0 is actually shifted to your Q3. This was a 1 here, right? Then let's continue at the clock 4, right? Then the last bit, which is the MSB, is shifted into Q3. Right, then at the 5th clock cycle, right, all data has been shifted out. Okay, now so what do we have at this point is that the following outputs, right, will be equals to 0, if you still recall that the input of the flip-flop 0, right, is connected to a AND gate, and this AND gate will become the output of this AND gate will become a 0 after the loading action becomes a shifting action, right? So that's about it for the 4 different shift register that we are going to talk about during the lab. Now there is still some other shift registers that we are going to talk about in the following lecture, right? So for now, this will be sufficient for your lab exercises or your practical on next week.